All right, welcome. Today we are getting into a really fascinating and sometimes frustrating phenomenon that every single RF professional bumps into sooner or later: tropospheric ducting. Think of this as your official field guide for spotting it when it happens.
So, just so you know, this is part 10 of our deep dive into RF propagation. It's a 20-part series, and it's all based on some incredible research from the RFI detectives over at Virtualization Options LLC.
Okay, let's paint a picture, one that might feel just a little too familiar if you've been in the field for a while. You're out on a job, and your readings, they just don't make any sense.
You're seeing a signal, and it's not just some faint ghost. It's strong, it's stable, and it's coming from a transmitter that's like 800 miles away. What's the first thing you think? Great, my gear's on the fritz, something is seriously wrong here.
But hold on. Before you start pulling out your hair and tearing down your equipment, what if the problem isn't your hardware at all? What if the culprit is something happening in the very air around you, creating a kind of invisible highway for that signal? And that brings us to the science of what's really going on. We're talking about something called an atmospheric waveguide. It sounds like science fiction, but it's very, very real. The official name for this is tropospheric ducting. Basically, under just the right weather conditions, our atmosphere creates a temporary duct. And this duct acts just like a physical waveguide, trapping radio waves and shooting them way, way over the horizon. We're talking hundreds, sometimes even thousands of miles. So how does this happen? Well, it all starts with something that's totally backwards from normal. Usually, right, you go higher, the air gets colder. Simple. But for a duct to form, you need the complete opposite. It's called a temperature inversion, where you get a layer of warm, less dense air sitting right on top of cooler, denser air near the surface. And here's the play-by-play. It starts with a nice, stable, high-pressure weather system. That system creates the temperature inversion: warm, dry air on top of cool, moist air. Now, that boundary where they meet, that's the magic spot. It creates a sharp change in the refractive index of the atmosphere, so any RF signal trying to escape into space hits that boundary and gets bent right back down towards Earth, essentially trapping it. Okay, that's the theory. But how do you, out there with your gear, know for sure that this is what you're seeing? Let's get into the practical side, your field guide. First things first, you have to rule out the other long-distance culprit, sporadic E, and they behave completely differently. Sporadic E is like a flashbulb. It's caused by ionized patches way up high, it hits hard and fast, and then it's gone, usually in just a few minutes. Tropospheric ducting, though, that's a slow burn. It gradually builds up, hangs around for hours, maybe even days, and then slowly fades away. So, here's your mental checklist out in the field. Are you seeing strong, steady signals from way over the horizon, like 500 plus miles? Are you getting weird interference on your local channels? Now, check the calendar and the weather. Is it summer or fall? Is there a big, lazy, high-pressure system sitting overhead? It's especially common near a coast or a big lake, right after a hot day cools off quickly at night. If you're ticking these boxes, you're probably looking at ducting. All right, so you think you've spotted it. Now let's talk about which frequencies are most affected, and believe it or not, how you can actually see this stuff coming. Now, while this has been seen as low as 40 megahertz, ducting really loves to party at the higher frequencies. We're talking VHF and especially UHF and microwave bands. Generally, anything above 90 megahertz is fair game, and the higher you go, the more efficiently these signals get trapped and propelled by the duct. And the thickness of that inversion layer is what decides the lowest usable frequency, or LUF. A really easy way to think about it is like a pipe. A thinner pipe, or a thinner duct, can only pass smaller, shorter wavelengths. That's your high-frequency microwaves. But a big, thick duct can handle those longer wavelengths, bringing lower frequencies like VHF into the game. And here's the absolute key takeaway. This is not a random glitch. Because ducting is driven by weather, and we can forecast weather, we can actually forecast the potential for ducting. It's a predictable event. In fact, there are tools built just for this. What you're looking at here is a Hepton Tropo Index map. A meteorologist named William Hepton developed it. It crunches all the weather data and spits out these forecasts showing where ducting is likely to happen and how intense it might be. For an engineer trying to manage a network, this is an absolutely priceless tool for getting ahead of interference. So we can identify it, we know the frequencies it hits, and we can even forecast it. But what's the bottom line? Why does this really matter in our day-to-day work? Well, for most of us in the professional world, ducting is a headache, a big one.
It's a massive source of co-channel interference. That TV station from 3 states away suddenly lands on the same frequency as your local transmitter, and boom, your service quality tanks and customers start calling.
But there's another side to this coin. For every engineer it drives crazy, there's a radio hobbyist, a DXer, who is absolutely thrilled. For them, ducting is a gift from the heavens. It's their chance to log unbelievably distant stations, using the atmosphere as a giant natural signal amplifier. It really just depends on what you're trying to do. And the physics behind all this is so powerful, so good at bending our perception of reality, that it hasn't just messed with radio waves. Over the centuries, it has literally created myths and legends. You know the legend of the Flying Dutchman ghost ship? Or how Arctic explorers would see entire islands and mountain ranges that just weren't there? A lot of those are thought to be a complex optical illusion called a fata morgana. And guess what causes it? The exact same thing as our radio duct. A strong temperature inversion bending light waves instead of radio waves. Just listen to this. This is what explorer Donald Macmillan wrote in 1913 after chasing the phantom crockerland for days across the ice. It's just a chilling reminder of how incredibly real these atmospheric tricks can feel, whether they're fooling your eyes with a phantom island or your receiver with a signal from 1,000 miles away. So that really leaves us with a final question to think about. As our RF spectrum gets more and more crowded every single year, are these atmospheric ducts going to become our biggest, most unpredictable source of interference? Or could they be our greatest hidden opportunity? The answer is probably a bit of both. The real trick is knowing how to spot it and when to expect it. Thanks for tuning in.